So on this first one, the function h of x is x plus 15 square root of x plus 15. So whatever you plug in for x, you add 15, then take its square root. So on part C, we have above that h of x is equal to the square root of x plus 15. So now we want to substitute x minus 6. What is h of x minus 6? So we are replacing this x instead of h of an x. We are replacing it with now an x minus 6. If you replace that x with an x minus 6, you replace every x, and it now just that one x, that single thing, is now an x minus a 6. Now, good habits would indicate that whatever you do, especially when you substitute negative numbers, or if you substitute more than one term, parentheses aren't going to hurt you. They're going to help you. So when you make that substitution, if it was a 4, 4 plus 15, 9, 9 plus 15, 23, 23 plus 15. So now this h of x minus 6 is the square root. That x is now an x minus 6. And then what do we do with it? You add 15. Not multiply, you add 15 to it. Because it's still whatever plus 15. So then you simplify. H of x minus 6 is equal to the square root. Parentheses first, inside the parentheses, x minus 6 is as simple as it's going to get. So you can drop the parentheses, and then you still have a plus 15. So you combine your like terms, and your h of x minus 6 is the square root. No other x's, but a negative 6 and a positive 15 is a positive 9. That's what h of x minus 6 is, the square root of x plus 9. Done. Can't go any further. Okay. Any further explanation or question or anything? Okay. This over here, left over here. So this time, yes, because what you're actually substituting in for that has an x in it. What I'm actually plugging in and replacing this x with has an x in it. So in other words, what we want to know is, we know what h of x is. It's the square root of x plus 15. So what's it going to look like if I plug in h of x minus 6? H of x minus 6 was now just going to simplify and be x plus 9, square root of x plus 9. So if I plug in 12 over here, 12 minus 6 is 6, the answer would be 12 plus 9, the square root of 21. Okay. Okay. Now, 12 minus 6 is like taking the h of just a 6, isn't it? H of 6, 6 plus 15 is the square root of 21. So that's how the connection is. Domain. And this is where I know there's some confusion going around between what I said and what you think I said. It's like, difference is she's always right. Get used to it, guys. Get used to it. That's when I get used to it. Just, your wife is going to be probably going to be right. I know I'm not right. I've been right for a long time. The denominator can never be a 0. The denominator cannot be, doesn't mean you can't plug 0 in. If I plug in 0, g of 0 is equal to 2 times 0 plus 1 over 5 minus 2 times 0. So 2 times 0 is 0, 0 plus 1. 5 minus 2 times 0 is 0. 5 minus 0, we get g of 0 equal to 0 plus 1 is 1. 5 minus 0 is 5. We get 1/5. That function is defined for x equal to 0, so therefore 0 is in the domain. 0 is fine. So what can we not plug in? That's the question. That's the most challenging thing about domain, having to answer a domain question. If I gave you solve, if I just said, all right, here's 5 minus 2x equal to 0, solve for x. Oh yeah, sure, no problem. Well, that's exactly what I'm about to do. But if I don't tell you, here, do this, and you have to think about it, that's the hard part. Or at least, I said this in my last class and it applies right now. When I first started teaching, you'll go through all the observations. And one of the person observing me corrected me in our post-observation talk saying, when you're teaching, when you're talking to students, never say that this is hard. Never work out a problem and say, this is the hard part, this is going to be hard. Never say that. Never say something's about to be difficult. Say it's going to be challenging. Look for the challenge. You play that mental game with it. A little bit of that is true. You gotta think. You're trying to hit the highest levels in mathematics. And if you are going to be a person who is going to head into the higher levels of mathematics, you got to be focused, you have to be disciplined, and you have to be a hard worker. And you have to realize sometimes the classes that were always easy may not be easy anymore. But that's why a class like calculus is a weeding class. It weeds out the ones who want to be doctors from the ones that will be doctors, from the ones that want to be engineers from the ones that will be engineers, from the ones that want to be architects from the ones that will be architects. Because in order to be an architect, you got to be able to pass calculus. And a lot of really, really smart people who are at the level ready to take calculus, they take calculus says, they take calculus, and they give up because it's not easy. What used to be easy, math, is no longer easy. And because they've never had to study for math before, they don't know how to study for math now. And that means they drop out and they change their major. The ones that have always kind of not always gotten it, but have worked hard or struggled or at least know to study, they're the ones that make it. Okay? They're the ones who overcome the obstacles. If they have questions, they don't care about asking them. That's what they don't care about. More than that incorrectly. They are not afraid to ask the questions no matter what. Remember, the person up here, our job is to help you. Now, I know not every professor takes that to heart. My job is to help. And I'm very lonely during office hours. And you guys are silent during, so weird. You guys are silent during class. So, here, domain. You can't have 0 in the denominator, you can't have a negative in an even root. So all that means is this denominator better not equal 0. So now you've got to solve for what x better not be. So it's kind of like instead of solving for what x is, you're trying to solve for what x can't be. It's the same process. It's the exact same process. Separate the number from the x. I'm going to add 2x to both sides. So I have 5 better not equal 2 times x. And then divide both sides by 2. So x better not equal, because if it does, it better not equal 5 over 2, because if it does, then the denominator would be 0. If I plug in 5 over 2, I get 2 times 5 over 2 plus 1 over 5 minus 2 times 5 over 2. So g of 5 over 2 is 5 plus 1 in the numerator. In the denominator, it's 5 minus the 2's reduced, and I'm left with 5. So I get 6 over 0, which is undefined. Which means the function, when you plug in 5 over 2, the function's undefined, therefore the domain can't have 5 over 2. It's got every other real number. No matter what you want to plug in, everything else works. But you can't use 5 over 2 because that gives me 0 in the denominator. So that means if you look at a visual, and I only do the visual to help you see what the interval has to be written on. You do not have to do the number line. There's 0. 5 over 2 is over here. 5 over 2 on a number line would have an open circle, and you can shade everything left and right, because everything except 5 over 2 works. So that means from negative infinity all the way up to 5 over 2, parentheses, union, the interval from 5 over 2, parentheses, to positive infinity. That's the domain. That's what you get to use from those intervals, any x value, except the negative, or sorry, except the positive 5 over 2. Okay. Domain questions are big, they're happy places where math professors like to go. Math professors like to ask domain questions, the higher levels. At least from my experience. They're always going to try to get you with a domain question. And with domain, you got to think. Can't have 0 in denominators. Can't have negatives inside and even right now, those are the things you have to be, looking for. If you don't have denominator with an x in it or anything that might make the denominator 0, all real numbers are going to be fine. If you don't have any even roots, square root, fourth root, sixth root, domain's going to be all real numbers. All right. Continuing with 1.4, we are doing number 25. So last week we went over the notes and definition of when is a function increasing, when is it decreasing, when is it constant, and the definition of when do those things happen. All they want in this question is determine the open intervals in which the function is increasing, decreasing, or constant by just looking at the picture. Just looking at the picture. And it's only about open intervals. We're not worried about closed intervals for increasing or decreasing. The only way you're going to have closed intervals, you have to have a solid point somewhere. Okay. So increasing is always about left to right, from left to right. is when the y's get bigger as you go from left to right. Decreasing, the y's get smaller as you go from left to right. Constant, the y's don't change. The y's are equal to each other as you go from left to right. So here's what the graph looks like. This is what it's doing. As you go from left to right, if you are going like a roller coaster, right now, the roller coaster cart would be climbing up the mountain. So you'd have to be going up like this. As you go from the x-axis left to right. Then you reach the top of this mountain right here. Once you reach the top, then you get to go wee all the way up. Go down this way. You're going down that first drop until you get to the bottom, and then you start to climb to go up the next one, and you're going up again. And it's as simple as up is increasing, down is decreasing. But again, it's about left to right. There are no closed points, and the directions even said open interval. So increasing, on, decreasing, on. It's increasing. I'm just going to go left to right on the interval from negative infinity until we get to what? Because as you can see, it's going up, 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 and then it stops. And at this point, it starts to go down, 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 down. So from negative infinity to what? 0. Remember, the interval that we're trying to describe is the x values. From what x value to what x value? It's increasing from x is approaching negative infinity that way, all the way, and it stops increasing when we get to that 0. So increasing, parentheses, always on infinity, from negative infinity to 0, parentheses. Open means parentheses, open interval. Closed means bracket. And then we decrease. We're going down. So it's decreasing from this x value, which is 0, and it decreases until we get to this point, which is what? What x value? 2. So from x equals 0 all the way to 2, it decreases. Open interval from 0 to 2. And then at x equals 2, it turns the corner. It reaches relative minimum, relative maximum, relative minimum. Then it starts to increase again. And it starts to increase from this x value, which is 2, and it's increasing forever to the right because we have no idea what else is happening. It's going from 2 to positive infinity. But that's not all. You need to make sure that you join these two intervals together. It's the union of those two intervals. Okay. And that's how you answer the question. Any question about it? That's 25. Yeah, so it increases. It's going up the curve, up the curve, up the curve from negative infinity. And it stops increasing when we get to this x value of 0. Okay. And then from this x value of 0 to this x value of 2, it's coming down the curve.
So I was just asking for the domain. It was just asking for the domain on this one.
No, it's not asking for the domain. It's asking for the intervals on the domain, pieces of the domain. And that's what an interval is. It's a little piece, little pieces of the interval, little sections. So from this section of negative infinity to 0, the graph increases. And then from 0 to 2, that little piece of the graph, those x values, the graph is decreasing, the y's get smaller. And then from 2 to infinity, the rest of the graph is increasing. The y's get bigger on that. So you're answering two different questions on what interval is the graph increasing, on what interval is graph decreasing. There's actually a third question, but it doesn't apply here. On what interval is the graph constant? And so to be constant, it has to be straight across. And we don't have that in this picture, but let me see if there is one. None of these have a constant in their picture. So none of them are connected with the line of the sugar. We'll come across one later. 33. Graphing utility. So I wanted to do 33 so you could see how to punch this up. We want to graph f of x is the absolute value of x plus 1, and then plus the absolute value of x minus 1. Go to my equations, y equals the absolute value function equals the absolute value button is here on the 84 under the math button. The absolute value of x plus 1, so I go to the math button. And the absolute value is under num, for numbers. Number functions. So I'm going to scroll one to the right. And it's the first option, ABS, absolute value. So I hit enter. And so it's ready to take the absolute value of, and the first thing I plug in is the x plus 1. So x plus 1. And then you got to close that parentheses. So there's the absolute value of the x plus 1. And then I want to add another absolute value of an x minus 1. So plus the absolute value of an x minus 1. And close the parentheses. Then you hit enter. Now, it doesn't say what window you should have, but the absolute value of x has its vertex at the origin, 0, 0. When you go plus 1, that's a horizontal shift to the left 1 unit. When you go minus 1, that's a horizontal shift to the right 1 unit. So it's staying right around x equals 0. So I'm just going to open up a window that goes, let's say, from -5 to 5 on the x-axis. And then what I'll do is I'll tell the graph, the calculator, to figure out the y on its own. So once again, window, -5 is my min x, +5 is my maximum x, x scale is 1, and then I'm going to hit zoom fit. Zoom fit will, now the calculator will figure out the y window to go with the x window that I put in, the x parameters. And so you can see it looks like we have a little straight line right here. Now that's kind of hard to really make sense of when you see these little dots and to tell what's really going on. The calculator, when I told it to do a zoom fit, it gave me the smallest possible Y values that fit the whole picture. So all I have to do is now go to my window to get a better idea. When did they tell the Ys to do? They told the Ys to go from 2 on the Y-axis up to a 10. Well, if I really want to see what's going on, if I could see the X-axis, that would be super. So I'm just going to change my Y minimum just so I can see what's happening to a -1 to 10. And that way I'll get a better idea. I do the zoom fit so I get an idea of what it will be, and then I can make an adjustment as necessary. That is one. And think about if you just plug 0, plug f of 0. 0 plus 1 is 1. Absolute value of 1, 1. 0 minus 1, we get -1. The absolute value of -1 is 1. You end up with 1 plus 1. When you plug in 0, the Y value is a 2. Everything between 0 and 1 is a 2. If I plug in 1/2, 0.5. 0.5 plus 1 is 1.5. What absolute value of 1.5 is 1.5. 0.5 minus 1 is -1.5. The absolute value of -1.5, sorry, I messed that up. 0.5 minus 1 is -0.5. The absolute value of -0.5 is +0.5. This was 1.5, that's +1.5, adds up to 2 in between. Get really close to this X is equal to a 1. That maybe 1.99, $1.99. 1. My bad. I'm actually giving the answer here. 0.99. So 0.99 plus 1 is 1.99. Absolute value 1.99 plus 0.99 minus 1 is 0.01. It's a penny. Negative. It's a negative penny. We take 99 cents minus $1. Absolute value of a negative penny is a positive penny. $1.99 plus 1 cent adds up to $2. For every value of X between 0 and 1, they always make a 2. That's why I go straight across. Same thing happens over here on the left-hand side. Okay. The questions that you're supposed to answer once you have the graph. So we're supposed to answer. Use the graph utility graphic. Determine the open intervals on which the function is increasing, decreasing, or constant. So as we go from left to right, we would be sliding down the curve like this. These Y values are getting smaller. And that's on the X-axis from -infinity all the way to -1, the y values get smaller and smaller. So it's decreasing here. Then from -1 to +1, all the y values are 2s. So it's constant on the open interval from -1 to 1. On the open intervals. And then when you get to 1, as you go to the right on the x-axis, the y values start to get bigger again. So it's increasing as you go from +1 to infinity. You have to be able to read the graph and interpret the question and information, and then be able to give that information to somebody else. Here's my graph. On this graph, it's decreasing from -infinity to -1. It's constant from -1 to 1, and then it's increasing from 1 to infinity. Okay? That's all you're supposed to do. Go to 7. Graph the function to approximate any relative min or max on the function. So on 37, it's -2 times x to the third. Now remember, when you do negative, you better not press your minus button. You got to press the actual negative button. Right here. -2x to the third. And I better delete the rest of this on that. Minus an x squared. And second. And then plus 14. So I'm gonna tell it to graph -5 to 5 again on my window. Right hit enter. So -5 to 5 is my X window, and then I'll hit zoom fit for the Y's. Okay. And we're supposed to approximate relative minimum, relative maximum. Now, you see how thick the y-axis is? So my x minimum, -5. My x maximum, +5. The x scale is put a little dash every 1 unit. So -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. What we had last in the y window, we told it to do -1 all the way up to 10. And we told it to put a little dash every 1 unit. The y scale was still 1. The y scale was still 1. Because the y scale is 1, it's putting a little dash every 1 unit. The reason why it looks so thick is because that y window, watch when I click on the window, goes from negative 205 down here all the way up to 155 up here. So on the graph, it's putting a little notch from negative 205 to 155. It's basically putting 360 little notches. So there's so many little notches that it looks like a big old solid line. If I change the Y scale, change that Y scale, and let's just put a little notch every 50 times. For every 50th number. Hit enter, and I hit my graph. And you can see now it's just putting a little notch at every value of 50. 50, 100, 150, negative 50, negative 100, negative 150, negative 200. Okay. I'm walking you through the graphing. I don't know how much experience you have in graphing calculus. So if you've got a lot, you're just kind of like, get on it. I'm getting it. All we care about is the max and mins. The relative max and mins. These go on forever. So there's really no absolute maximum because it's way up there. And as soon as you think it's at 4,397, it's still going up. There is no absolute max. Same thing. There is no last bottom number down there. But we've got a bottom here, relatively speaking, in this neighborhood, relative minimum. Looks like we got a little mountain, a little hilltop right here. Relatively speaking, that is a relative maximum. And it looks like these relative minimums and maximums are going to happen within, that's -1, -2, that's -3, -4. So I don't need to go to -5. 1, 2, that's a 3, that's a 4. And if this is -50, that's +50. I can change now the window to get a better visual of those maximums and minimums. So -4 to 4. So we change the Y minimum to -50. The Y maximum to +50. And that way, I'll put the Y scale now at every 10. Looks like it didn't go down. Oh, my Y minimum is not a -50, it's a -5. So. Okay. So now you get a better visual of where the maximum are. -50, -40, -30, -20, -10, 10, 20, 30, 40, -1, -2, -3, -4, 1, 2, 3, 4. So it looks like the relative minimum is between -2 and -1. Looks like the relative maximum is between 1 and 2. It looks like the relative minimum is about between, it's basically between -10 and -20. And it looks like the relative maximum is between 10 and 20. So here's how you find it. Gotta go to bigger mode. Right here, don't trace. Tracing is not going to tell you the better answer. Calc. Blue, the trace button, which activates the calc, you can hit blue for a second. So second, and then hit the calc. And we want to find the minimum. Option 3. Let's find the minimum. Now you have to tell the calculator where to look. It's just not going to give you the answer because you might have more than one minimum. You might have a graph that does something like this. Then you got these two relative minimums. Which one do you want to find? You have to tell it where to look. So now it's asking for left bound. So left bound means I'm thinking the minimum is right about here. So I need to take the little cursor and I need to put it on this side of where I think the minimum is. So just basically to the left of the -2. And then it's going to say, what's the right bound? So I need to put the cursor on the right-hand side. I need to tell it where to look for the minimum. Between what two values? Between this x sub 1 and that x sub 2, it's going to look for the minimum. So I'm just going to move the cursor with the little buttons right here until I get to the left-hand side. And now I can tell right here, I'm on the left, I'm less than -2. I'm to the left of -2. I hit enter. Now I need to go to the right. So now I move the cursor to the right. I kind of want to be close to a 1. And I could have told it to look from here to here realistically. I could have told it to look from here all the way over to here. They would still find that minimum because that's the only relative minimum in that interval. I just want to be a little bit right there. By enter. And then I've never understood this next one. Guess. It's like, do they want me to guess or do they want me to ask the calculator to guess? I don't really get it. So I just hit enter one more time. And it says the relative minimum is at x equals negative 1.703256. The y value is negative 16.8641. Because remember, there's an ordered pair. Okay. This is huge. This is huge. This is where people get messed up on a calculus class. It's asking you for the relative maximum and minimum values. Could have asked you for what value of x does a maximum or relative minimum occur. It didn't say for what value of x. It didn't say find dx. It said what is a relative maximum and minimum value. That's the whys. What is the maximum of anything? You want to know what comes out. What is the maximum cost? Well, that would be the answer to whatever you plugged into a function, the y's. So the maximum or minimum values is the y value. If they want to know when does it occur, that's your x. That's your x. Where does it occur? That's your x. If they ask for the ordered pair, well, then that's simple. They give you a pair. But you get two things when you use a calculator. You get the x value and the y value. Most times students should just put the x. When they really are asking you what is the maximum value or the minimum value, they want the y value. So if we look in the back, the answer is going to be negative 16.86. Oh. I really wish they would like label the tops of the pages so I know what section I'm in. The heck number is it? 37? 37. Well, shiver me timbers. They want the ordered pair. Then why didn't you write the ordered pair? Good thing it's only home. I will be very specific. I don't like it when they just leave it, ambiguous. And then you do the same thing to find the max. Okay, second, count. Maximum is the number 4. You got to tell it where to look. I can hit enter right now because I'm on the left-hand side of the max. Now I just got to get all the way over there to the right-hand side of the max. Now, here's a shortcut. I can use the cursor and move the cursor to the right-hand side, or that's 1, that's 2. The max is here. So it's somewhere between here and 2, isn't it? So this is my min, my left bound. I want 2 to be my right bound. So guess what? I'm just going to hit 2. Right bound equals 2, hit enter. And I don't have to do the cursor. So 1.369924, comma 12.160394. So technically, when I do left bound, right bound, I know it's somewhere between 1 and 2. I just hit left bound, punch in a 1, hit enter. Right bound, punch in 2, hit enter, and then hit enter again for the guess. It'll give you the maximum. Okay. Sometimes I take you down the long road so you appreciate the shorter cuts. Because there's no way to appreciate a shortcut unless you've done the long. That was 37, 47. How to use a calculator? I'm punching in the step function. Sketch a graph of the function by hand and then use the graphing utility to verify. The greatest integer function, step function. So the step of x plus 2. And then I'm going to also do 49. F of x is equal to the step of x minus 1. And then minus 2. Graph by hand. Now I'm just pulling up the calculator's screen so I have a window to work with. I'm just going to go -2, +4. And scale of 1 on the y-axis. -3 all the way up to +2, my bad. -3 up to about 6. And for my y scale, I'm actually going to put a little dot and a nudge to 0.25 every quarter. All I need is this. That's all. So 1/4, 1/2, 3/4, 1, 1 1/4, 2, 1 1/2, 1 3/4, 2, 2 1/4, 2 1/2, 2 3/4, 3, 2 1/4, 3 1/2, 3 3/4, 4. Negative 1/4, negative 1/2, negative 3/4, negative 1, negative 1 1/4, negative 2 1/4, 2 and negative 1 1/4, negative 1 1/2, negative 1 3/4, negative 2. And then this is 1, 2, 3, 4, 5, and 6. Negative 1, negative 2, negative 3. This is 1/2. 3 over 2, 5 over 2, 7 over 2. Negative 1/2, negative 2. So they want us to sketch by hand. So here's the hand, we're sketching by hand. You have a table. Plug it in x's into f of x is equal to the step of x plus 2. Step of x, the greatest integer such that it is less than or equal to x. The greatest integer that is less than or equal to the number you're plugging in. Okay. So if I just start with negative 1, I'm just going to use negative 1. So that f of negative 1 would be the greatest integer that's less than or equal to negative 1, and then add 2. The greatest integer, integers, positive and negative whole numbers. The greatest integer that's less than or equal to a negative 1. So what's the answer? So you have, right here, you're plugging in negative 1. Here's your integers, negative 2, negative 1, 0, 1, negative 3. The greatest integer that is less than or equal to this thing. Negative 1. The greatest integer that's less than or equal to negative 1 is negative 1 equal to. So that means this is negative 1 plus 2, which is 1. We plug in negative 1, we get 1. So that's a solid point right here. At negative 1, we get positive 1. And then let's creep in a little closer. Let's plug in negative 1/2. So the step of negative 1/2 plus 2 equals. So when you plug in negative 1/2, negative 1/2, there's your negative 1. Negative 1/2 is right here. We want the greatest and the biggest integer that's less than or equal to the negative 1/2. Well, the only integers surrounding my negative 1/2, the only integers possible is the negative 1 or the 0. Those are the only integers that are a possible answer. The biggest integer that's less than or equal to this negative 1/2. Which one is it? The greatest integer that's less than or equal to this. Which one? Negative 1. So less than, so it's got to be to the left of the negative 1/2. And that's the biggest integer that is less than the negative 1/2. It's not 0 because 0 is not less than negative 1/2. So you get negative 1. This is negative 1 and then a plus 2. Negative 1 plus 2, we get 1 again. So a negative 1/2 is an x. The answer is 1. So we get this point right here. If you plug in negative 0.01, a negative penny. So the greatest integer that's less than or equal to a penny, a negative penny, plus 2. So a penny would be right here. It's still in between a $- and 0. So what's the biggest integer that's less than this negative penny? -1 again. So this is -1 plus 2, and we get +1. So at a negative penny, we still get a +1. So it's like right, another solid point right there. But when we get to 0, when you actually plug 0, the greatest integer that's less than or equal to 0 plus 2. Well, the next biggest integer that's greater than or equal to a 0 is 0. So now you have 0 plus 2, so the answer is 2. When we plug in 0, we get a 2. So that's up here. So what happened to the, that first piece that we were graphing? It was doing this. Every single answer from -1 up until 0, the answer is a +1. Then when we get to x is 0, it jumps up here. So the graph is broken. So at the end of this step, you have an open circle. It's an open circle at the end of that step because the next step takes over at 2. You can't have 2 closed circles. If you have 2 closed circles, that means when we plug in 0, the answer here is 1 and the answer up there is 2. We get 2 different answers, and that's no longer a function. So it can only have 1 answer. At the end of the first step, you for an infinite number of numbers, you're going to get +1. But as soon as you plug in 0, the answer is 2. And then for every number all the way up until 1, think about it, 1/2. The greatest integer that's less than or equal to 1/2 plus 2 is 0 plus 2. So when we plug in 1/2, we get 2. Everything from x equals 0 up until x equals 1. All of these answers are going to have y values of a 2. Right here, when we plugged in 1/2, we got a 2. But when we get to 1, the greatest integer that's less than or equal to 1 is 1. 1 plus 2, that gives me 3. So when we get to 1, it jumps up to 3 with a solid point. X is 1, y is 3. So that means what happened to the previous step, everything equals 2. Just as soon as we get to 1, there's an open circle, and then it picks up there. And then everything between 1 and 2, all of those steps are going to be equal to 3 until we get to x equals 2. When you get to 2, it's going to jump up 1 step, and you're going to get a solid point right here at 2, 4. And it's going to be solid all the way up until we get to 3. When we get to 3, it's going to jump up, and we're going to get a 5. Solid right there at 3, 5. And it's going to be solid all the way until 4. We're going to close open circle right there. And then it's going to pick up at 4. You're going to have a closed circle, and it's going to go all the way that way up until you get to 5, and then it'll jump up again. On this side, between -2 and 1, what does it mean? What's going on between here and here? Think about you're coming this way, down the steps. So what would the Y value be on the next step down? Huh? I'm sorry, my brain, my ears back. Well, that means you're going to go from a positive one and you're going to go down to here. How many are you going down every time you move a step? That's a 5. You step down, it's only a 4. You step down, it's only a 4. You step down, it's only a 2. Every step, you're only coming down 1. So when you take a step to the left off of this step, where would we be? We'd be right here at 0. And it'll be an open circle just below there, and they'd all be there. Okay. Now, how do we type this in the calculator? We go to now. Now, so I gotta go to my equations, y equals. I go to now. And under numbers, let's see. I believe it is number 5, integer. Number 5. Integer of x, close of parentheses, and then plus 2. I hit enter, and then I hit graph, and there's my steps. So that integer, the int function in the calculator, this is called the step function, but it's the greatest integer function. So it's under int. Right? Yes.
So when we're graphing it out, when we are writing about it, do we just use whatever number we can?
Yeah, because you're setting up your own values that you're plugging in on the x-axis. So you're picking, you know it's going to change every integer. So you would want to pick something in between to see what happens in between. Because there is a way to tweak this where they're still broken, and that's what a step function is. At every integer, it's broken. You have a discontinuity. But there is a way where the steps, have you ever seen, like, in a movie when they have the trick stairs, they're walking up the staircase, somebody throws a lever and all the stairs go slanted and they slide down instead. There is a way where these steps can go slanted. And that just means we're going to tweak something inside the function. If you go 1/2 x inside, that can tweak the slope. Or maybe a 1/2 x on the outside. That now changes it. We have a slope going on based on the values. So there is a way to do that, and we have to explore that. We're not there yet. We're just getting used to it. Now, on 49, this is a really good chance for me to explain what happens in section 1.5. So it's kind of like a precursor preview of 1.5 and what's going on there. F of x is the step, and inside you have an x minus 1, and then outside you have a minus 2. And you're supposed to graph by hand. Well, I'm going to go straight to, here's how we read this information, kind of like basically the shortcut. In section 1.5, we're going to learn about the transformations of graphs. The vertical shifts, the horizontal shifts, anything that's going to make it go upside down versus right side up, anything that might narrow it or widen it, those kinds of things. When you mess with the x's, when you mess with the x values, that means you're going to make a shift left and right. If I add or subtract to the x's, then after I plug in the number, it's going to change. The parent function, and we talked about that before when we first started. The parent function is just this, plain old simple greatest integer of x. Kind of like, that plain cheese pizza, nothing on it, no toppings. When you start adding toppings, you start messing with x, start messing with y, you start multiplying by something, maybe put a negative, put it upside down. You start asking for all sorts of crazy stuff. But the plain version of a step function is just simple step of x. Step of x is just going to be right here. When you go from 0 to 1, everything in there is just going to be a 0. And then when you get from 1 to 2, everything in between 1 and 2 is going to be equal to a 1. Everything between 2 and 3 is going to be equal to a 2. Bare bones. Everything between -1 and 0 is going to be a -1. Everything between a -2 and a 1 is going to be a -2. What we just did over here is we took the step of x, and when we added 2 to it, we took all the old y values and we added 2 to the answer. So that shifted this up 2 units and put it here. It shifted this from -1 on the y-axis. It shifted it up 2 units and put it here instead. Everything rose because you added 2 to all the old y values. If you mess with the y's, if you add something, you're going to move it up. If you subtract something, you're going to shift everything down. So this problem, all the y values are going to shift down 2 units because you have a -2 outside of the actual function. Inside here, it's normally, get rid of this, it's normally right here when you plug in 0. When you start messing with the x's, you're going to go left and right. What would make x -1? Again, this is going to the, I'm not solving it, but I'm asking a question. What would make x -1 equal 0? What would x have to be? At x equals 1. At x equals 1, this thing equals 0. This original parent function likes to start at normally just where is 0? Well, we're not going to get 0 unless we're at x equals 1. When you plug in 1, it's like taking the step of 0. +1, +1. Look in there. You see -1, but where is the answer? At positive, it shifted 1 to the right. You see minus, but it went to the right. You're doing the opposite of what you see. You see a minus, it's going this way, to the right. If it was x +1, if there was an x +1 in here, when does x +1 equal 0? When x is? Our next is -1. Right, when x is -1. If x is -1, -1 + 1, it's like taking 0. That's where the parent function likes to begin, when you plug in a 0. But that would be a -1. -1 behaves like 0 does. So that means when you plug in -1 to the left, even though you see plus, it's shifting left. You're doing the opposite of what you see. So when we do these kinds of expressions, It's going to be f of x minus an h. And that negative is built in. It is built in. It is like, y sub 2 minus y sub 1. You subtract the y's when you do slope. X sub 2 minus x sub 1 and not you subtract. It's built in. It's always going to be the opposite inside the function. So therefore, when you see plus, even though you see plus, the shift is to the left. If you see x minus something in there, minus, you think, oh, minus is that, it's shifting to the right. You do the opposite of what you see. H stands for opposite. So the building blocks are this. What we're going to do to the parent function of f of x equals the step of x is now going to be f of inside is going to have an x minus h, and then on the outside is a plus k. And the h is the horizontal shift, left and right of the graph, and k is the vertical shift, up and down. Inside, x minus, you do the opposite sign for the h. So when I see it was -1, then I know that my regular step of x, the h is a +1. The opposite is +1, so it's shifted to the right. And k has a plus in front of it. So for k, you keep the sign. H, you do the opposite. K, you keep the sign. So this k is a -2. So it's going to shift down too. So this would be our simple parent function. Here's the parent function, the step of x. So the parent function would look like this. I'm going to do it very lightly. From -2 to -1, so close, and then very lightly, open, and then close, and then open, and then close, and then open, and then close, and then open, step, basically step like open, close, and then open. That's just without no toppings, regular plain cheese pizza. And this is, again, a little preview of 1.5. It actually gives you some of the work you're doing in 1.5. X -1. So now we're going to take every single one of these, and they're all going to shift over 1 unit. So this solid circle would shift over to -1, and the open circle would shift over to -2. And then you got to take 2 away. You got to drop it down 2 units. -2 take away 2 is down here at -4. So it wouldn't even be on there. This is going to shift to the right 1 and shift down 2 units. So this point is going to be here, and then it's going to have an open circle here at 1. This is going to go 1 to the right, and it's going to shift down 2. So it's going to be closed here, and it's going to have an open here too. This is going to go to the right 1 and shift down 2. So if you're at 1, when you go down 2, you're going to be at -1. This is going to shift 1 to the right and shift down 2. So from 2, you're going to be down here at 0. So it's going to be a closed circle and then an open circle there. That's how it's going to work. So what I had in my picture is now going to graph here. And what I'm actually going to do is I'm going to graph both. So I'm going to graph plain old, good old cheese pizza. So just the step of X. And now I'm going to graph the second one is going to be number, the greatest integer of X minus 1. Close the parentheses, and then -2. Enter. So you're going to see something graph right under the green, and then the second one they'll graph right under the red. I guess you can't see it because it's right under the x-axis. That's how you graph. Yes.
So do you want us to actually graph it on? Or
Well, here's the deal. You got to get used to drawing these things. So you got to get used to actually physically drawing these things because that's what I'm going to have to see on a test. So if you don't actually practice drawing them and you show up for the test and you haven't practiced, that's where you let yourself down.
I just wanted to know how they work. You want
So,
to see.
well, let's see. Basically, I'm not going to hold you to any more than what the homework asks from you. Homework says, sketch it by hand and then verify with the graphic calculator. Which, guess what? I did. I did a little bit extra because I did the original parent function so you can see how it shifts. Because I just lectured on 1.5. You didn't even know it. How painful, how painless was that? It's like getting a shot till you look the other way.
You mentioned that for like graphing this, it's just whatever works with the graph, like whatever number you want to put in.
Yeah, because you got to plug in to help you figure out, does it go to, if you're going to get the point right. And I mean, your test score points. I'm talking about where is it going to go on a y-axis. Just mentally you can do it, but you still got to draw it. So if you're sketching it by hand, you don't have to do the table every day, unless you need to. I mean, if you're just copying, so here's the deal. You're supposed to sketch it by hand first, then verify with a graphing calculator. So graph it without a graphing calculator and see if you can actually do it. Okay. And I don't need 1,000 points. I just want to see some steps. Put your steps in. I know here's what I'm hearing. What's the bare minimum? So I don't mean to interpret it that way, but that's how it's a little bit coming across. All I'm saying is I'm going to hold you accountable for answering the test question. And if you're not able to answer it because you haven't graphed it for yourself, that's where I got to, that's where it's going to fall apart.
I'm just trying to figure out like what exactly you might want.
Well,
I don't want to like mess it up. So.
Well, right. Okay. So then I want to graph by hand and then check whether you graph utility. You don't have to do anything except, can you plug it in to check? That just is good. Now you're learning to use the technology, but there's no work to do on the homework from the graphing calculator. The checking it is for your benefit. Did you get it right? Remember, when I had to do these things for myself, back in the Stone Age, we didn't have the graphing calculators. Or if anybody did, they were, $300, $400. So that was not me. We just had simple solar scientific calculators, and we just needed to know what was happening. Which technically I didn't. I mean, graphing to me was a foreign language because nobody approached it with, again, the language part, but nobody said it's that opposite shift. Or maybe they did, but it just didn't click. It just didn't click for me. That shift of the H is the opposite of that sign. And all you got to do is know what the graph basically looks like. And then it's going to go in the opposite direction of what you see here, if there's something in there. And then up or down based upon the number that comes after. Now, there's other things to consider, but we'll put those pieces in. The little parts of the puzzle. Okay. And then always will have a practice. Nine, 87. Okay, 57, you're supposed to graph by hand. Graph the piecewise function by hand. Okay, and I chose 57 because it's square roots. Graphing paper. So the piecewise function, you have to just, when you see the word piecewise function, that's exactly what you're dealing with. Pieces. You're dealing with pieces, one piece at a time. So we have f of x is equal to the first piece, square root of 4 plus x. And that's if you have x's that are less than 0. So for any x that's less than 0, you do that. And it's equal to the square root of 4 minus x if you're using x's that are less than 0. Oops, greater than 0. Let's get this right. Greater than or equal to 0. So when I have a piecewise function, whether it's 1 piece, 2 piece, 3 piece, 4 piece, where the domain has its breakup from x's that are less than 0, you do this. That's the first piece. Then the second piece is defined for x's that are greater than or equal to 0. So where the domain has got a little break in it, right here at x is 0, you have the left-hand side for all these x's that are less than 0. On the left-hand side is 0. F of x, which in other words, remember, this is the same as y. Y is equal to square root of 4 plus x. So when you're on the left-hand side of 0, you're plugging it into this first piece. On the right-hand side of 0, when x's are greater than or equal to 0. For the right-hand side of 0, you're going to use y is equal to the square root of 4 minus x. You, again, Sorry, I'm gonna use that curse word. Think, you gotta think. Especially when you're dealing with square roots. When you're graphing, we like to graph nice numbers. We like to plot, 1, 3. We like to plot 1, -4, -4. We don't want to plot decimals. We don't want to plot, if we can avoid it, fractions. We certainly don't want to plot, x is 5 and a y of square root 3. We want to plot nice, happy numbers. So when you're graphing square roots, you're going to want to be looking for, on camera, you're going to want to get the only nice perfect squares that you come across. The square root of a 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 gives you 3. The square root of 16 gives you 4. The square root of 25 gives you 5, and so on. You want to take the square root of perfect squares so you get nice, perfect answers that come out, so you can plot them nicely and easily. Okay? If you have any control. So on this side, for all the x's that are less than 0, y is equal to the square root of 4 plus x. So, first thing I would think about is, I want to make 0. I want this to be the square root of 0. I would like the square root of 0, please. So what would x have to be to give me a square root of a 0? -4. What would make a square root of, what would make 0 on the inside? What would make 4 plus x equal that 0? It would have to be 4 plus x equals 0, subtract 4. X would have to be a -4. So the first thing you do, let the x equal a -4. Y is the square root of 4 minus 4, or plus -4, which is 4 minus 4. Square root 0, which is 0. So when you plug in -4, 0 comes out. But -4, the y is a 0 right there. And if it's on the x-axis or y-axis, like I told you, you do not need to put an ordered pair when you label it. Perfectly fine with you just writing -4. One thing, if it's on the x-axis and y-axis, you don't put parentheses around single numbers. You put parentheses around an ordered pair, not a single number. So I take off the point if you do that. So it's like labeling a number. Now, here is the next thing you might think to do. If you try to go to the left, remember, you can't plug in negative numbers or square root of x. If you try to go with this, let x equal just to the left, -5. We're at -4. If you try -5, we get the square root of -5 plus 4. That's the square root of -1. That's not allowed. So let's, again, think the domain. For 4 plus x, 4 plus x has to be greater than or equal to 0 as a domain. If you subtract 4, all of the x's that you try to plug in here have to be greater than or equal to a -4. You can't go to the left of -4. You can only plug in numbers to the left. Okay? But you can't go all the way to the left. Remember, this left-hand side is only good for x's that are less than 0. So you can go up to 0, but you can't plug in 0. So let's just keep thinking. The next nice number we'd like to go 1. So we now like to take the square root of a 1. So inside you have a 4 plus x. What would x have to be to give you a 1? What would x have to be? -3. Remember, you're just going to go 1 to the right. So if we let x equal -3, y is the square root of 4 plus -3. So that's the square root of 1, which is 1. So at -3, we get 1. Now, because that's in quadrant 2, you do have to label it with an ordered pair when you turn in a test or a quiz, if we're graphing. Now, remember I told you we like nice numbers? If you just keep going 1 at a time, so hey, I use 4, -4. I went 1 at a time, I went -3. Let's try -2. Let's keep it up. Y is equal to the square root of 4 plus a -2. That's the square root of 2. Not a nice number, not a perfect square. Now, it is graphable. It's 1.414, but it's an unending, non-terminating, non-repeating decimal. You'd have to estimate it as a little bit less than 1.5, but you got to label it with the square root of 2. How about you just go for a nice number? So I wouldn't use something that wouldn't give me a nice number. The next nice perfect square is a 4. We'd like a 4, please. Kind of like baby Copperfield or what is it? Orphans. I like a 4 plus x equals a 0. Oops, my bad. 4 plus x equals a 4. I like a 4 in there. So what would x have to be? 0. Subtract 4. Let x, oh, but here's the deal. This is good for only x's that are less than 0, not equal. But y is equal to the square root of 4 plus 0. Square root of 4, which is a positive 2. So when you, because you don't get to use the x equals 0, at this point, when you graph it, it's going to be an open circle. Right here, it would have been right there if you could use it. And the graph goes up and stops right there. It gets infinitely close to that spot. It just cannot use that spot. The analogy is this. If you have x equals 0, you have 2 sides of a fence. You got 2 nasty neighbors that live next to each other. One side, one set of the neighbors, they actually built the fence. They own the fence. So they get to sit on the fence. On their side, when you plug in 0, they're going to have a solid point when you plug in 0 at that point. They get the solid dot, wherever that is. But you guys, or my guys, or whatever, we didn't build the fence. We don't own the fence. We can get infinitely close to the fence, but you better not touch it. We touch the fence, it's not our fence, they're going to see the dot. So you put an open circle right at where it would be if we could. And that would be everything from -4 all the way to the 0 except the 0. That's what the left-hand side looks like. On the right-hand side, think about it, 4 minus 4, it's going to be like this. You'll get a solid right there. It's going to fill it in on the right. It's going to fill it in, and then it's going to go down like that. It's going to be the other near side. Okay. All right. I am going to take a roll because you don't want here. Actually, I've got roll taken care of because whoever didn't get the quiz back didn't hear. So I will see you guys on Thursday. For being here. You guys are working or whatever.